Okay, welcome back. Chapter 3.4 is measure of position. In particular, we'll be talking about standardizing a little bit. So diff is the case that when you have particular values, by standardizing, can we figure out where these particular values are positioned? So as an example, I brought my own kids example here. So my two older kids, their name is Junye, Minu. When you have a kids, they actually have this height charts, and then they kind of follow where their height is located, and they give percentile and stuff like that. But anyway, when they were a year old, 12-month-old, my daughter was 72.1 inch and Mina was 28.5 inches. And it is known that it is pretty symmetric, and the normal shape, their height, the baby's height, with the mean of 29 inch and standard deviation is 1 inch. So just looking at the number, because of mean is 29, you can say that Junie was a little taller side and Mina was a little shorter side, right? Then my question is, where their actual location exactly? Again, percentile is one way they will actually give you some ideas, but at the same time, we can use slightly different ways as well. So here we're introducing something called standardizing. So standardizing is pretty much for your X original value, and you subtract the mean of it and divide it by sigma. So you kind of scale it a little bit different, and we call that Z, and that's a standardizing. That process we call that standardizing. So your original X become a Z value, Z score, we call that. So what it means is it kind of scale it and so that it is easy to look at it. That's all it does. So for example, in the last chapter in 3.2, we talked about empirical rule, right? So here is your mu in the center. There's a mu plus sigma, mu minus sigma. There was 68% of data set is there. And mu plus 2 sigma, mu minus 2 sigma, there's a 95% and 99.7% in 3 sigma, kind of things that we talked about. Let's kind of figure out what it would happen if you actually standardizing it, change it to the Z. So if you do for here at this point, your X is mu, right? So if you do mu minus mu over sigma, that value will be actually equal to 0, right? And same way, if you do the mu plus sigma as X, this point become 1. This point become 2. This point become 3. This point become -1. This point become -2. This point become -3. Right? So any value, if you actually standardizing it and change it to the Z score, there will be I guess 99.7% of the data set will be between -3 and 3. So if you calculate the Z score, it will be a little easier to figure out where your data set is actually located. Okay. So going back to our example, so what it does here is, for original data, our mu is 29 here, and then standard deviation is 1. So here will be originally probably looking like that, 28, 27, and 26. This particular one, the standard deviation is equal to 1. So the scale, the shape itself probably aren't going to change at all, because the Z score also has a standard deviation is equal to 1. But what had happened when you change it to the Z score, you're going to have 0 here, 1, 2, 3, -1, -2, and -3. And then for the particular point, for example, 32.1, if you standardize it, your z-score will be 32.1 minus your mu, which is 29, divided by 1, which is 3.1, right? So once you know what your z-score is, you kind of already know that this particular score, 32.1 inch, is right there. So right there. So pretty tall, pretty extremely tall. You can actually say that. On the other hand, the other person, Minu, 85, the 28 minus 28.5 minus 29 over 1, which is negative 0.5, right? So this one will exactly give us another position. The Minu will be right there, right in the middle there. Let me right in the middle there, right? So rather than just, oh, that looks tall, that looks little, it actually will give you exactly the position is, and in a scale that you can kind of already have, okay, -3 to 3, -2 to 3. So you have a little bit better sense of where the location exactly is. That's one of the ways that you can use the z-score. We're gonna come back to this z-score concept, and we're gonna use this concept in chapter 7 again. Okay, for the next one, I kind of briefly mentioned it already, but the percentile. So percentile definition is just the set of data is value such as kth percent observational less or equal to the value. So whenever I actually think about percentile, I mean, here's another, this graph actually tells us as well, but when you think about percent, the number you think about is 100, right? So when you have a distribution of the data, you can kind of imagine it. You kind of divide your data set so that everything has a 1%. So here's a 1% data, 1% data, 1% data. So since this one is, if you go in the middle, will be taller, so you're gonna be probably more and more skinnier here. But anyway, you can do the similar things here as well, right? So 1%, the last one is 1%, and then this one is 1%, right? Okay, so the first one is first percentile, second one is second percentile. This one will be 50th percentile, okay? And then the very last one will be P99th percentile. There's no P100 because you're actually dividing the probability of it to 100, each 1%. So the last one is actually P99. So if you think about in this picture, on the right-hand side, what it shows us is when we are saying the 50th percentile, which means you have this point that has a 50% of data set is on your left-hand side, and 50% of data set is on your right-hand side. Hey, wait a second. We kind of knew what that is as well. We learned, we talked about it in 3.1. What was the point that has a 50% of data and 50% of data? The median, exactly. So median is also the 50th percentile is exactly what the median is. That's the same thing. Okay, so that's the percentile. Then what would be the quartile? When you think about quart, you think about 4, right? Number 4. So just like a percentile was 100, a quartile is 4. So you're dividing your data set into 4 equal area. So out of 100%, if you divide it in 4 equal area, you're going to have 25, 25, 25, 25% there, right? And then for the dividing point is called first quartile, second quartile, and third quartile, Q1, Q2, Q3. So if you think about it, this first quartile is exactly same as 25th percentile, right? So 25% of data is up to there, up to that point. 50th percentile, 75th percentile. But these are exactly same notation, same thing. And once more, 50th percentile or second quartile, there are median. It's the same as median. Okay. And now we learn all those things, and then let's see the Z-score you probably cannot get from the StatCrunch, but let's get the Q1, Q2, Q3 in our class survey data. We played with the socializing hour for the on-campus and off-campus before. So this is actually going back to, let me see. Blackboard. Go to Blackboard. Again, once more, here is my StatCrunch you can find. Where's the StatCrunch? StatCrunch, and once more, I'm gonna get that data set, the class survey data set. I need to sign in. Okay, so that one was what we were playing with. Okay, but that's our class survey data set. Once more, we go to stat and summary stat column and hours of socializing. Where is the socializing? Here we are. Okay, and we were talking about on and off campus. Okay, and I'm just going to compute it. Okay, that's exactly the same process we talked about the previous sections. So here we are. Now we talked about the mean and standard deviation. Now it is asking what's the Q1, Q2, Q3. So here is the Q1 value for on-campus student socializing hour, 7 hours. And Q3 is 20 hours. Then what would be Q2? When there's no Q2 provided here, right? But Q2 is actually exactly same as median. So here is your Q2 median 15. So 7, 15, and 20. So if you go back here, you can say P1 is 7. No, not P1, Q1. Sorry. Q1 is 7. Q2 is 10. Q3 is 14. Is that right? Let me double check. Median is 15 and 20. I was totally wrong. 15 and 20. This is 7, right? Right? 7 and 15 and 20. Okay, so there are those are the values for Q1, Q2, Q3 values for of socializing hours for on-campus students. Okay, thank you.